Hello, today we're going to go over Chapter 8.4 in AP Chemistry on electron configurations. An electron configuration is just a way to represent the arrangement of electrons in an atom. It tells us where the electrons are at outside of the nucleus. So some examples for sodium, it has 11 electrons. Okay, and we are going to fill up the energy levels starting with the very first energy level. So if you'll remember, we have our nucleus in the center. We have the first energy level, which is just an s orbital, so it's 1s. And then we have 2s surrounding that in the second energy level. And another sublevel of energy level 2 would be the 2p orbitals. Okay, so we have 2s, then 2p, and they're very close to the same energy because they're in the same energy level. And then we would have 3s at a higher energy. And after 3s would come 3p, and then it starts getting complicated because the 3d and the 4s go in the reverse order. So let's go ahead and do these simple ones right here. So we would put our two first electrons in this first energy level. So sodium would begin with 1s2, first energy level. So this is the energy level. And then the orbital, okay, so the s orbital tells us that it's a spherical shape. This is the orbital. And then this top number tells us how many electrons. So this is the number of electrons in that orbital, number of electrons. So there was 2 electrons in the first energy level, and they are in that s orbital. That's what this is telling us. Once that's full, it will only hold 2 electrons, as do all the s orbitals. We have to move out to the second energy level. And the second energy level starts with 2s, and it's also going to have 2 electrons in it, and then it's full. Then we go out to the 2p orbitals. 2p, the p orbitals, remember we had an px, a py, and a pz orbital. Okay, they're in the x, y, and z axes. And overlapping all 3 of them, we would get kind of a flower shape. Each of these orbitals, each of these orientations holds 2 electrons. So that's 2, 4, 6 electrons in these 2p orbitals all together. And that's why we have 6 electrons there. Okay, so when I add these up, I get 4 and 6 makes 10, and there's one more electron to place. It has filled up this 2p, so it's going to move out to the 3s, and we have 1 electron left. It will hold up to 2, but we only need 1. So this is the electron configuration for sodium. Chlorine is a bigger nucleus. It has more protons and therefore more electrons. It has 17 electrons in it. I'm just going to go ahead and copy what we have here because it's going to fill in the exact same order. They always fill from lowest energy level to higher. 2s2, 2p6, 3s2, and then we're going to move out to after 3s would be 3p. Okay, and so this would be 10, 12. I have 5 more electrons, and we know the p orbitals of any energy level will hold up to 6, but we only have 5. So I put my 5 there, and then it's filled. Okay, potassium, we need to look up on our periodic table. Potassium is in group 1, and it has 19 protons. Its atomic number is 19, so that means it has 19 electrons. So 19 electrons. We always start with how many electrons. And let's look at bromine while we're at it. Bromine is the one we're going to do next. Bromine has 35 electrons. All right, so let's fill up our 1s, 2s, 2p, 3s, 3p, and now I would have, there's 10, there's 18 electrons. I have one more. It's going to go in the very next energy level, which should be the 3d orbital. But because electrons do not follow our rules, they just follow the lowest possible energy. The lowest energy orbital that they can fill is the 4s. So it's going to be 4s, 1. That one lonely electron means potassium has a valence electron of 1, and it's right here in the 4th energy level. Okay, so the 3d orbital is skipped. The 4s happens to be a less pricey version, so it's going to fill that first. And bromine, 35. So I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Let's count our electrons. Here we have 10 and 10, so we're at 20. We still have 15 more to go. After the 3s comes 3d10. Okay, so there's 10 more. After that, then we're going to go back to this 4th energy level, 4p6. So that's 10, 20, 30. Oops, 36. I went too far. So this 6 should actually be a 5. Okay, and then I would have 35 electrons, and we are done with that electron configuration. We're going to do a lot more of these. If you've forgotten how to do them, do not worry. All right, so the off-bow principle tells us that an electron occupies the lowest energy orbital that can receive it. And that's the reason that it's going to fill up the 4s before the 3d, because it's the lowest energy. It's not necessarily the closest to the nucleus, but it has lower energy than this 3d. Okay, so whichever one is lowest energy, it will fill that first. The Pauli exclusion principle tells us that no two electrons can have the same set of quantum numbers. Well, it kind of looks like these two electrons have the same set of quantum numbers. They're both in energy level 1. They're both in the s orbital. There are 2 of them in there. The last thing that can be different between them is that one will be spin up and the other will be spin down. Okay, so that is how they are different. The spin quantum number is going to be different for those 2 electrons. And lastly, Hund's rule says that each orbital of a particular energy level gets 1 electron before you pair them up. So if I have the p orbitals, these little lines are representing my 3 p orbitals, each of these will get 1 electron in it before I pair them up. Okay, so if I'm drawing the orbital notation, you'll see in a second, they each get 1 electron. I would not put 2 electrons together when there are 2 open orbitals that are empty. Okay, it's like sharing a bedroom. Usually, if there are extra bedrooms, children do not want to share. They want their own before they have to pair up. If you are out of bedrooms, they have no choice. Then they have to go back and share. Okay? And electrons are added to these orbitals based on their energy, like we were saying, which is similar to price. You're going to see in a second. So they're going to fill up whatever costs them the least amount of energy. But when we go back and we remove electrons to make ions, so like potassium, for example, will lose its outer electron, this 4s, they are going to lose electrons based on the energy level. The highest energy level is the one that you're going to lose electrons from because it's the farthest from the nucleus, which means it has the least force of attraction to that nucleus. That's Coulomb's law. Okay, we're going to look at the off-bow hotel to look at those prices here. Okay, so in our off-bow hotel, we have different levels of our hotel. There are 4 levels. It actually goes up to 7, but for this hotel, this one just has 4 levels to it. Okay, so energy level 1, 2, 3, and 4. And among those levels, we have various priced packages. So the S is our suite. These are the lowest price packages. And then we have our P, which is the penthouse, a step up from the suite, right? Then we have our deluxe rooms over here. And lastly, the fantasy suites. So these are the highest energy ones that we can have on here. Down here, this is how they are arranged based on their price. So if you want to stay on the tippy top floor in the fantasy suite, that is going to be the highest price. Okay, this ground floor s orbital is going to be the lowest price, the lowest energy. Okay, so here's the price schedule. And this is just based on observations. This is the actual order that electrons will fill up these orbitals. So our nice little system of giving them numbers like 1, 2, 3, and 4, and letters like S, P, D, and F, they're not always going to follow our rules. Okay, our rules are made up. We are imposing our order and organization on these electrons that kind of do what they want. So this is the order that they fill from lowest energy or price to highest. So it starts with 1s, then 2s, then 2p, then 3s, then 3p. And here's where it flip-flops. That 4s is just slightly lower in energy than the 3d, so it's going to fill up first. And then it will go back and fill up that 3d orbital. Okay, these 3d orbitals, there are 5 of them. After 3d, then you're at 4p. After 4p, then you're at 5s. And after 5s, now we go back to that 4d and fill that up, and then back to the 5p. Okay, so the order of these, you're going to see in a second, there's a way to remember them. There's a little chart that we're going to use that actually helps us recognize the order that these fill in. So you do not have to memorize this, okay? You do not have to memorize. Don't memorize this because there's a way for us to remember it. But you do need to know that that's why they are filling up these orbitals in this order. Okay, it is because of their price. Now, when we go to remove the electrons, if we had electrons here, let's say, and here, which ones are going to be removed is kind of a tricky thing. So even though these are higher in energy, these 3D, so they're just slightly above the 4s, when you're taking electrons away, you don't go by the price. You don't go by the energy. You go by the energy level or how far from the nucleus it is. So you would remove from the highest number energy level. So this is energy level 4 versus energy level 3. You're going to remove these ones. So these are added first, but they're also removed first. Okay, so here is that little trick that I was telling you. Don't memorize the orbital notation because this setup helps you remember electron configuration. So you just write out 1 through 7. Okay, so to repeat this pattern, you would put 1, 2, 3, 4, 5, 6, and 7. And then you're going to have all of your S's because every energy level has an S. And then P, only the second energy level and down, has a P orbital. Okay, remember the number of different orbital shapes that each energy level has corresponds to that energy level. So S and P is all the second energy level has. Energy level 3 has S, P, and D, as do the following energy levels. And then for F, because the periodic table only needs 118 spaces, we only need the 4F, the first one that can have an F orbital. S, P, D, and F, there are 4 shapes because of its energy level 4. And then once we have 5F filled, we will have the 118 spots that we need. So we don't need these. They are still there. 6F and 7F are there, but we don't need them, so we don't write them. Okay, now how these fill up is you're going to start with energy level 1s. And then you're going to go to 2s. And after 2s is 2p, and after 2p is 3s. So this is a neater version. I'm going to switch over to here. You're going to fill them up in this diagonal order here. Okay, so 2p, 3s, and then 3p, 4s, 3d, and then 4p, and then 5s. So you're filling them up based on these diagonal lines here. Okay, and that's why you don't have to memorize the order down here for our orbital notation. You can just follow these arrows and you know what order to go in. So for example, let's do bromine again. Bromine, where can I write it? I'll write it up here. Had 35 electrons in it. So I'm going to start with 1s and put my 2 electrons there. And now I go to 2s and put 2 electrons. And then 2p comes next, and it holds 6 electrons. So we do have to remember that the s orbitals hold 2 electrons. the p orbitals hold 6 electrons, D holds 10 electrons, and F will hold 14 electrons. Okay, so where were we? 2p, after 2p comes 3s, 2, and then after 3s would come 3p. Okay, 3p holds 6 electrons. Let's count up what we have. There's 10, 18, so after 3p is 4s, 2, and after 4s comes 3d, 10. Let's count. Whoops, I'm out of space there. That's a 10. So now I'm having 10, 20, 30. I have 5 more electrons, and after 3d comes 4p. It will hold up to 6, but I only have 5 more to put. So that is 4p, 5, and then it is filled. So that's how we use this to help us with electron configurations. This little chart, you follow the diagonal arrows to fill up the energy levels. All right, orbital notation. We are going to, instead of just writing 6s and remembering that 6s holds 2 electrons, we're going to actually draw a line for 6s representing that 6s orbital, and it will hold up to 2 electrons. So I could draw 6s, 1 up, 1 down. Those would be the outer electrons if it was a 6s, if the 6s was filled. Okay, so we are going to do an example. Let's start with an easy one. Let's do nitrogen. Okay, nitrogen has 7 protons and 7 electrons. So we're going to add arrows to our orbital notation until we get to the number 7. So I'm going to add 2 electrons on every line. There's 2, 4, and here is Hund's rule. Every electron gets its own orbital unless we have to pair them up. So that was 4, 5, 6, and 7. So nitrogen, you can see, has 1 electron in each of those p orbitals, and we would call these unpaired, or I'm at a loss for words. We would call these unpaired electrons. So it has 3 unpaired. And that is why nitrogen tends to make 3 bonds, because atoms can come in and pair these up and make those 3 bonds. Or if I have 2 nitrogens, it tends to make a triple bond where they're sharing these electrons to fill up these orbitals. Okay, so nitrogen between itself makes a triple bond, and then I have these lone pairs over here. All right, so this is orbital notation. Let's do sodium. Sodium in A had 11 electrons. So here's 7, 8, 9, 10, and 1 more would go right here, 11. So this shows us that the very outer electron on sodium is in this 3s orbital, and it has just 1 unpaired electron out there. Right? Lastly, so that's orbital notation, and I can get the order that this fills from low energy. So this is energy increasing up this way. From low energy to high energy, I can get the correct order of these orbitals from my electron configuration chart right here. Okay, so it would go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So you can just write the lines. Every s gets 1 line, every p gets 3, D gets 5 lines, and then F, like you can see here, 4F has 7 lines for its 7 different orientations. All right. Lastly, the noble gas notation is where we use the periodic table as a cheat sheet. So we just need to know that the period corresponds, in most cases, to the energy level. Okay, so the period over here, these are almost always numbered. This is the period. Going down tells us the energy level. Let's write it over here. Period equals energy level. which we denote with a lowercase n for energy level. So this would be energy level 1, right? Energy level 2 and 3 and so on. And then we need to know the blocks. So this was our S block. This over here is our P block. Over here in the center is the D block, and down here is the F block. Okay, so in other words, this would be 2S that these are filling up. And since I have two columns here, the alkali metals and the alkaline earth metals, the first column has one valence electron in this s orbital. So if I was talking about lithium here, it's going to have 2s. 1 is the last part of its electron configuration. Moving over here, this would be 2p1, and then if I move over, 2p2, and we're going to go all the way up to 6, 2p4, 2p5, and lastly 2p6. And then if I went down below it, it would be 3p1 through 6. So every time you move over in that block, you're adding an electron to that orbital. Okay, so this would be 4p, 1 through 6, 5p, 6p, and 7p. So this very last electron that we just discovered and named oganesson is going to end with 7p6. I know that's the end of that electron configuration for oganesson. Okay, just as an example. The D block, just to confuse you a little bit, remember that the S orbital is filled first, and then you go back to the previous D orbital. So this would be 4s right here that is being filled, and after that actually comes 3D. So this D block is off by 1 from the period. So the energy level of the D block is 1 less. So this is 3D, then below that in period 5 would be 4D, 5D, and period 7 is the 6D orbital. Okay, and then remember right here, we actually cut the periodic table and removed this section. So these two belong right here, and they are off by 2 from the period. So this is 4F. It's 2 less than this period 6, and this one is 5F. And this fills 1, so 4F1, all the way up to 4F14, because it can hold up to 14 electrons. And so below it would be 5F14. And every time you move over on here, you're adding 1 electron to this F, to these F orbitals. Okay, so let's do some examples. Chlorine has 17. Let's look at where it's at on the periodic table. So chlorine is right here. It is in period 3. Okay, so it has filled up all of the interior energy levels. And it has also, so anything we cross over in order to get to that element, so in order to get to chlorine, we cross through the 3s, and then there is no D block for right here. So it goes from 3s over to 3p, and we're moving over 1, 2, 3, 4, and 5 places to get to chlorine. So chlorine is going to end with 4s2, because we had to cross through 4s2, and then 3p5. What comes before all of that, before the 4s? So to get to chlorine, we've crossed through this 4s. Before sodium is neon. So we're going to write the noble gas that comes before our element. So before chlorine, we have neon with its 10 electrons. So the noble gas notation for chlorine includes neon and all of its electrons, in addition the 4s2 and the 3p5. Okay, so that's what this is going to show us. All right, let's do arsenic. Arsenic is right here. It's number 33. It has 33 electrons. The noble gas that comes before arsenic is argon. So let's write argon and all of its electrons. Okay, so all the electrons in argon are assumed to be filled, so up to 18. After argon, number 18, comes potassium, number 19, and it has 4s electrons. We're going to cross all the way across this 4s orbital here, so it's going to be 4s2, 4s2, and then to get to arsenic, we have to cross all of these d electrons. So the 3d orbitals are completely filled before we get to our our arsenic over here. Let me select it so I don't confuse myself. So it's 3d10 because we've gone all the way across. 3d10. And then lastly, when I get to this side of the periodic table, I am back into the fourth energy level. So this is 4p, and then I have 1, 2, 3 electrons in that 4p orbital. So 4p3 is what it would end with. So those are the 3 ways that we denote electron configurations. This is called the noble gas notation. It's a shorthand way of writing them that uses the noble gas and all of its filled electrons and just shows you the outermost electrons, which are very useful when we're going to talk about bonding. Okay, then I have the orbital notation that helps us understand which electrons, which elements are going to be magnetic, diamagnetic, paramagnetic, based on their electrons. We're going to learn that next chapter. And then lastly, we have the full electron configuration, which I have seen on the periodic table, where they want you to write all of the orbitals out completely, just like I did here for bromine. You would write them all out. Okay, so those are electron configurations, and we are done with chapter 7 and the beginning part of chapter 8.